where we're at is going over the unit circle and making sure you understand how to draw that, how to use that, and then after that we'll do properties. A lot of people have asked me, Josh, do I need to use the unit circle? Can I just use special triangles? You can use either one. Special triangles, unit circle are all going to get you to the same place. All right? In later classes, it kind of depends on your teacher which one they're going to reference. Right? I always reference the unit circle because that's how I memorized all the information about trig. So it doesn't hurt you to at least be familiar with both the unit circle and the special triangles approach. But today we'll finish up talking about how the unit circle helps us, and then we're going to do identities, properties of trig functions. Okay? So that being said, I'm just going to jump right in. If you guys have questions at the end of class, I'll be happy to answer. Okay, but for now, I want to make sure we finish this. So 6.2, unit circle. So the unit circle is any circle, a unit circle is any circle with radius 1. The unit circle is the circle centered at 0, 0 with radius 1. Do you remember the equation for the unit circle? X squared plus y squared equals 1 is the equation for the unit circle. So on this picture that I've drawn, we drew this last time. On this picture that I've drawn, the radius of this circle is meant to be 1. So every little ray here from the center to the edge of the circle is length 1. Now, I've put on here all the rays that correspond to special angles. Okay. So what I mean is I started at 0, if you focus on the purple rays, I started at 0, and then I went 1/4 pi and put a ray. And then I went another 1/4 pi and put a ray. And then I went another 1/4 pi and put a ray. Quarter, 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 quarter. So these are all your pi over 4 reference angles. Meaning that this little portion right here left over is pi over 4. This little portion is pi over 4. This little portion is pi over 4. So the purple comes from splitting the pi into 4s and then labeling them. Okay. The blue comes from splitting your pi into 6 equal sectors and then labeling that. Right? 0 pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6. And keep going. So the rays come from taking your special angles and just propagating them all the way around the circle. Remember, well, I don't know if you remember, but I gave you the definitions, the new, kind of new, definitions of sine theta, cos theta, tan theta, all of these things. Do you remember what these were? Let's start with sine theta. Yeah, so usually sine is opposite over hypotenuse. But then we went on and we expanded that definition and said sine is y over r. But in this case, because r is equal to 1, sine of theta is just y over 1, which is equal to 1. Cosine of theta is x over the radius, which is 1, so that's just x. So the nice thing about the unit circle is sine and cosine are just the x-coordinate and the y-coordinate on the circle. And then you go in and there's a bunch of definitions for all these things, y over x, then you flip them all, x over y, 1 over x. So according to the unit circle, those are the definitions of our 6 trig function. So what we're going to need to make any sort of use of this is the x, y values at all these points here. At every point where you have a special angle, you want the x, y value to make the most use of this diagram. And I showed you at the end of class, I showed you a little trick to remember these x, y values. And of course, you can develop your own memorization scheme. But the axes are easy. Okay, the axes are exactly what you think they are. You look at it, this is, because it's radius 1, this is 1, 0. Because your circle's radius 1, this is 0 on the x, 1 on the y. Radius 1, but to the left, negative 1, 0. Radius 1, but down, 0, negative 1. Okay, so those are all of your points on the axes. And for these middle points in here, just remember 1, 2, 3. Okay, you start with the y value going up. The y values go 1, 2, 3, and then going down, you do 1, 2, 3 again. Then you have to divide everything by 2 and square root the tops. There's no point in square rooting 1 because the square root of 1 is 1. So those are the points, and that gives you your x and y values in the unit circle, which you can then use to find things like sine of pi over 6. Right? Looking at this, what's sine of pi over 6? 1/2. Why? It's the y value. That's our definition. Sine of an angle, sine of pi over 6 is the y value on the unit circle. Now, we did this, but we didn't label the other points. In general, I usually don't even label these points because it takes a lot of time, and the only difference between these numbers and these numbers are signs. S-I-G-N-S. Okay? So as far as conserving your time, you might not want to label these every time you use or draw the unit circle, but let me show you how to label them so you know how this works. All the x, y values are going to be exactly the same as these x, y values. Meaning I can put 1/2 root 3 over 2, root 2 over 2, root 2 over 2, and then root 3 over 2, 1/2. So I'm copying these x, y values. The only thing that changes is because we're in the second quadrant, one of them is negative. What's negative in the second quadrant? So these are all negative. And then you flip down here. Okay, it's the same. You think of it as a reflection. These two match up, these two match up, these two match up. So you'll have root 3 over 2, 1/2. Then you'll have root 2 over 2, root 2 over 2. And then you'll have 1/2 root 3 over 2. But because we're in the third quadrant, both of them are negative. Finally, either you flip these guys down here or you flip these guys over here to get your values in the fourth quadrant. So let me go down like this. Root 3 over 2, 1/2 will be my first point. Root 2 over 2, root 2 over 2. And then 1/2. Because we're in the fourth quadrant, y is negative. Right, so we're going down, so y is negative. There's the unit circle. With all the special angles and all the points labels. Like I said, if you're working on a test or a quiz, I wouldn't draw this whole thing. Some of you will. Some of you will have other methods. Okay, but what I do if I need to find sine and cosine is I simply draw a little schematic like this, where I label these axes because that tells me a lot of information and it's really easy to do. And then I label my 3 special angles in the first quadrant with 1, 2, 3, 1, 2, 3, over 2, over 2, over 2, over 2, over 2, over 2, root, 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 root. But I don't bother with these because I know all that does is change signs. So this has all the interesting information on it. And it didn't take me more than 30 seconds to draw. But now let's actually try to use this, okay, so you understand exactly how it works. So use the unit circle to find the exact value of each expression. So I want you to tell me what the sine of pi over 4 is. Should be easy. If you have this picture in front of you, or even this picture in front of you, you just go to pi over 4, and you say sine is the y value, root 2 over 2. So to find sine of pi over 4, you go to pi over 4 and look at the y value. Easy peasy. Root 2 over. Over here, you notice I didn't label the angles, but you kind of have to know this is pi over 6, pi over 4, pi over 3. You can label those if you want, it just takes a little more time. But the denominators go up, or go down. 6, 4. All right, what about b, cosine of 2 pi over 3? You go to 2 pi over 3 on the unit circle, boom. Cosine is the y value? X value. Oh, I had that mixed up. So cosine is the x value, which means cosine of 2 pi over 3 should be negative. You gotta be a little careful with this one here. Tangent of negative 5 pi over 6. So yeah, you can either break tangent down into sine over cosine, or you can think of it as y over x. Right, that's the direct definition. So if you can find where negative 5 pi over 6 is, you just do y over x. But how do I find negative 5 pi over 6? You go backward, right? You go down when you start counting your angles. Start from 0, but because the angle's negative, go negative 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So if you're going negative angles, you have to count it. This angle here is negative 5 pi over 6. Because I counted it. 1, 2, 3, 4, 5. And then I go and I find my x and my y. Tangent is y over x. So over here in my definition, I'll put negative 1/2 over y over negative root 3 over 2 is x. Then I have a fraction over a fraction, which is disheartening. So I flip and multiply. Negative 1/2 times 2 over negative root 3. Certainly some simplification happens here. 2 and 2 goes. The negative over negative will become positive. So it's 1 over root 3. Absolutely rationalize that. Multiply by root 3 over root 3. And it becomes root 3 over 3. If I were to make, well, first of all, questions about how about that? Yes?
I'm trying to understand how you got the very last part, like the 1/2, and you started canceling, but where'd you get the positive 1/2?
I changed the negative. Right? It was
Oh, I get it. It's division.
negative over negative becomes, well, yeah, that's from here to here.
That's what I was wondering
Yes,
about.
yes, I flipped this and multiplied. One other useful thing while I'm out of here is the values of tangent. It's kind of tedious, okay? So it might be worth your time to memorize the values of tangent. Tangent only has 3 values, and they're not hard to remember for these special angles here. And it always increases, so tangent starts with the fraction, so I'll write it in the green here. Tangent at a pi over 6 reference angle is root 3 over 3. Tangent at a pi over 4 reference angle is 1. And tangent at a pi over 3 reference angle is root 3. These are your tangent values. So you could always get those by doing y over x. If you did root 2 over 2 divided by root 2 over 2, you'll get 1. And if you did root 3 over 2 divided by 1/2, when you flip and multiply, you'll get root 3. And if you do 1/2 divided by root 3 over 2, you'll get root 3 over 3, like you'll get over here. Except the negative, but they can't. So you can get all of these by doing y over x, but if you have a little extra room in your memory banks, it might be worth remembering that the tangent values increase as you go up on the circle. So they go root 3 over 3, the fraction, then they go 1, and then they go root 3. So you just get that way you don't have to waste a whole bunch of time doing y over x. But, yes?
Are the tangents the same in the other quadrants, except you gotta change them from?
You gotta change signs.
Yeah.
So, like in the other quadrant, you would do root 3 over 3, 1, and root 3, right, going up, they increase, but they need to be negative.
And then quadrant 3, they'd be positive.
They'd be positive, yeah.
or negative.
Right, because here you have a negative over negative, so yeah, tangent will all be positive. Here they'll all be negative. Yep. So maybe the trickiest one of the bunch here, part D. Cosecant of 23 pi over 4. So cosecant is the reciprocal of sine. Right? Cosecant and sine are reciprocals, so I know this is going to be 1 over 1. But the whole trick is I have to figure out what my y value is at this angle. So I go, how do I figure out where 23 pi over 4 is? I would probably change it into a mixed number. That'll save you a little bit of heartache. 4 goes into 23 5 times with a remainder of 3. So I'm going to go to 5 3/4 pi. Here's 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Then I have to go 3/4. 1/4, 2/4, 3/4. So 5 3/4 pi ends up going around a bunch of times, 2, 4, 5, and then it goes 3/4. Which means for my evaluation here, I'm focusing on this ray and this y value. So I'll put 1 over negative root 2 over 2. Or the reciprocal of root 2 over 2, negative root 2. Of course, that's not simplified, that's ugly. So how do we make that look a little prettier? Fraction divided by a fraction with a multiplier. So this becomes 1 times negative root 2 over 2. I'm sorry, 2 over root 2 negative. But 1 times anything is the same thing again. Although that's still kind of ugly, still kind of hard on the eye. So you rationalize. Root 2 on top, root 2 on bottom. Gives you negative 2 root 2 over 2. 2's cancel and you get negative root 2.
It's the hypotenuse of these ones.
On the unit circle, yes. That's what we mean by the unit circle. So, however you want to evaluate these, I don't care. But you have to be able to get them proficiently and accurately and quickly. Okay? So if you want to use triangles to do this, great. Right? If you just, I don't know, have everything memorized in a table or something, fine. But you're going to be expected to know these things, be able to come up with each of these in about a minute or less. So
be able to do it.
Questions? No? Okay, good, perfect, lovely. Before I get to the identities, the properties part, which is, hopefully we'll get to spend 45 minutes on that, I want to talk about, well, first of all, these axes. Right? So each of these axes, these angles are all multiples of pi over 2. Right? So what I mean is, if you look at this diagram, for example, the first time you hit an axis, actually the first time is right here at 0 radians. But then as you go up, you get pi over 2 here, you get 2 pi over 2 here, which is pi, you get 3 pi over 2 here, and then you get back to 2 pi. So the axes give you, just by drawing a circle and labeling only the points on the axis, you can evaluate sine and cosine for any multiple of pi over 2. So what I mean is, suppose I had none of this. Gone, all gone. Like it never existed. Vanished from the face of the earth. Unit circle? What's the unit circle? That's what most of you are thinking right now anyway, right? Understood. So, if I ask you, for example, to find sine of 3 pi over 2, what I would think and what I would do in my head is I would either imagine or draw this circle. I would figure out where 3 pi over 2 lands. Since it's a multiple of pi over 2, I know it's on an axis. 3 pi over 2 happens to be right here. I label this point, and then I can tell you sine of 3 pi over 2 really quickly. It's the y value. Took me like 30 seconds. So what happens, especially in later math, the books tend to use these multiple of pi over 2 angles because they're so easy to evaluate. Right? Most people could evaluate these without doing much work or without having to remember much. So hopefully you understand what I'm saying here. When I give you an angle that either has a 2 in the denominator or has no denominator, it's going to land on one of these axes, and you can evaluate it really quickly just by figuring out which axis it is. Right? So if I give you cosine of 5 pi, so this doesn't have a 2 in the denominator, but it still lands on an axis. This is like 10 pi over 2. Where does this land, actually? 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So 5 pi is going to land here, which you know has a point of what?
-1.
Negative 1, 0. So cosine of 5 pi, x value, right? Cosine is the x value. So you get one of these angles that lands on the axis, there's not a lot of work to do. You just figure out the axis and then you know your answer. Sometimes what will happen, I might give you something like this. What happens with tangent of pi over 2? Where's pi over 2 land? Y-axis, right? Straight up. Pi over 2. So my x and y values are 0, 1. Tangent, though, is y over x, which is 1 over 0. Uh-oh. 1y, 0x, 1 over 0 is tangent. That's undefined. So tangent's undefined at pi over 2. You can't divide by 0. You cannot have 0 in the denominator. It's not. one more sort of theoretical example here about the unit circle. I told you what sine and cosine are. Sine of an angle and cosine of an angle. On the unit circle, sine of the angle is equal to the y value, and cosine of the angle is equal to the x value. Cosine and sine and tangent and cotangent all are functions. Okay? Functions, if you remember how functions work, they take in an input and they give you an output. So in this case, the input of sine or cosine is an angle. Right? You input an angle, pi over 4, pi over 3, pi. And then you output the y value on the unit circle. So, y value. So the purple is the input, the blue is the output. So my question, which is the next example, is what is the domain and range of the sine function? Of the function f of theta equals sine of theta. Right, so this is function notation. F of theta represents your output, theta represents your input. In general, what do domain and range mean? Do you remember? So x and y is one way to think about it, but I would encourage you not to think about that because we have x's and y's here and it might get confusing because they mean different things. So instead of domain and range being x and y, think of it as input and output. Okay. Domain is the set of all possible inputs. Range is the set of all possible outputs. So for sine of theta as my function, the domain, because theta is the input, the domain is all possible angles. Okay, so the question for domain is what kind of angles can I put in here? Or let me turn that around. Is there any angle I cannot take the sine of? Is there any angle that's, when you put it into sine, sine says, ooh, I don't know, undefined.
The one we just did.
That's not sine though.
Oh.
That's not sine. If I were asking tangent, you'd be right on.
If r is 0 or less.
Well, r is 1 for this definition always. So my question is, on the unit circle, can you draw for me a theta where there is no y value? Where y makes no sense? No. Every theta you draw, I will have a y value to look at. Right? If you draw me a very small angle, I'll have a y value to look at. If you draw me a very big or a very negative angle, I'll have a y value to look at. So no matter which angle you draw me, somebody walked in and saw this picture that they got drunk. What are you doing? No matter which angle you draw me, I can find a y value. So the domain for sine, all the possible angles, all real numbers. Negative infinity to infinity. If you give me any angle between negative infinity and infinity, I can find you a y value on the x. Range is a little different. The range is a little more tricky. Well, maybe not tricky, but a little more confined. The range is all possible outputs. The range is every y value you can get out. So is there a way to draw an angle on the unit circle so that you get out 5 as a y value? No. What's the highest possible y value sitting on this unit circle? 1. The highest possible y value you get is going to be right up here. This guy has the highest y value. And it's equal to 1. What's the lowest possible y value you can get out of the unit circle? This guy's the lowest. And it's equal to -1. So the range for sine, the outputs, the answers you can get for sine, go between 1 and and negative 1. Or you can write it as an interval like this. This means all the numbers between negative 1. This is kind of a precursor, okay, if this is blowing your mind, it's okay. We're going to graph these functions, and once you see the graph, that's another way to get the domain and range really easy. But it's here, it's something to think about. What do you think changes for cosine? You may.
How come the domain's not negative 1 to 1?
That would be saying that the only angles I can put into sine are negative between negative 1 and 1. But for example, I can put pi into sine. Sine of pi makes sense. I just go to pi on the unit circle and I look at the y. So the domain represents the angles that you can put in here.
So if you're looking at the circle, it could be everything infinity to the left and to the right?
No, it's not left and right. It has nothing to do with left and right. It has everything to do with angles. It has to do with how much rotation you can go. I can go any amount of rotation. I can go any amount of rotation, forward or backward.
Oh, okay.
Cosine is actually the same domain and range. Cosine you can put any angle into, and the x and y for cosine